Welcome to this lecture series in real analysis. We are starting a new module which will be devoted to developing the theory of integration, Riemann integration in particular. And since this is a new module and we are not going to use, at least for this lecture, not going to use much of what we have learned previously. So let's not recall anything. Okay. One very simple problem for practice. And now let us get started. So what are we trying to do? We're trying to develop a theory of area of planar figures. So our high school geometry experience gives us or teaches us how to find areas of such things. Oops, I meant to draw a polygon. Doesn't matter. So we can find areas of triangles, of quadrilaterals, of pentagons, polygonal figures. We are also taught the formula for the area of a circle, even though that is a very sophisticated matter and will be something that we will discuss later. But as of now, we can find areas of polygonal figures. Can we somehow develop a theory of area which is more robust, where we can talk about areas of curved things? So the theory of integration that we are going to develop is not going to reach as far, but it will do a pretty good job of satisfying some of that. So what we are going to do is develop the theory of area under the curve of a function. So for instance, if we have the graph of the function that we have depicted here, the domain being a closed interval, then we can talk about the area trapped between the curve and the x-axis. Assuming the function is sufficiently nice. Not all functions behave well enough for us to be able to assign a value to this region, but a very large class of functions will have that property, and it will satisfy the usual algebraic relations that we expect areas to do. So for instance, the area under the curve, when you restrict the function to the left part and the right part, they add up to the area under the curve of the total. So it's not a meaningless theory that we will develop. It will satisfy basic intuitive facts that we need of area. Okay, and you must have seen this in your physics experience. Integration is what we are going towards, and you must have seen some of it in your high school physics. Anyway, so let's proceed. All right, so now we start with definitions. So we have the closed interval a comma b. A subdivision of it is defined as a collection of finitely many points, all lying within the interval, and it is an ordered sequence of finitely many points. So when I use the word sequence, please don't confuse with what we have learned previously. We have defined a sequence in this manner. We talked about convergence and whatnot, but here when I say a sequence, I just mean an ordered something. So a subdivision of a comma b is an ordered list of finitely many points. All of those points are from this closed interval with two requirements, that the first point or the 0th point in that ordered list is the left end point of the interval, and the last element of that ordered list is the right end point of the interval. So formally, a subdivision of the closed interval a comma b is a finite list of n things, n is some positive integer, where or such that the first guy is the left end point of the sequence, the last guy is the right end point of the sequence, and in between we have these inequalities. Alright, so I hope the definition is clear. We have just collected or marked out some of the points in the interval. The first one is the left endpoint, the last one is the right endpoint, and there is a natural ordering in them. Very simple definition. But note that even though we have defined it as an ordered list, any finite subset F of the closed interval with the property that the left and the right endpoints are in that finite subset will naturally give rise to a subdivision of the closed interval. So let's see an example to illustrate what I'm trying to say. Suppose we have the closed interval 0, 1. And we have some finite subset of it. So let's say F is 0, 1/3, maybe 1 upon root 2 also, and maybe 3/4 and 1. So this is a finite subset of the closed interval 0, 1, which contains the left and the right endpoints. How do we get a subdivision out of it? Well, pick the smallest element here, which is obviously going to be the left endpoint. So this will be A0. This is A0. Then we have the next smallest element, and I believe that is going to be this guy. Which one is smaller amongst the two? This is smaller. So 1/3 will be somewhere. I think it will be here. So that will be A1. What is the next element? This is taken care of. This is taken care of. Which is smaller amongst the two? I believe it's going to be this. Let's see. It is. So 1 upon root 2 is the next one. And it will be somewhere here. So this is A0. That is A1. That is A2. This will be A3 and this will be A4. So any finite subset of a closed interval which has both the left and the right endpoints naturally gives rise to a subdivision, and occasionally we will think of such a subset as a subdivision, because unnecessarily then we would be introducing a notation or some sort of a correspondence between them. But since it is so clear already, there is no need to be too formal about it, right? So we will be nimble with these two pictures. All right, now we will associate some measures or some numbers to a subdivision. Fix a subdivision sigma. Typically, subdivisions will be denoted by sigma and tau and rho. So fix a subdivision sigma of the closed interval a comma b. Define Li of sigma as a number. Which number? You go to, suppose I is equal to 1. So I better be a positive integer. I should have written it. I'll write it. So suppose I is equal to 1. You go to the first element of the subdivision and ask what is the length of the chunk that it is the right endpoint of. If I were equal to 2, go to the second guy, ask what is the length of this chunk. For A3, what is the length of this chunk? For AI, or sorry, for I, you go to the ith element, ask the length of this chunk. So what is this? This is equal to, we are defining it as AI minus 1. So it's this length, the thing that I'm shading. Okay, so this we define for all I from 1 up to n. Okay. And the norm of sigma, which we denote like this, will be defined as the smallest amongst all these numbers. Smallest or largest? I myself am confused. Largest. Largest is what makes sense. It's the largest of all of these. Right, so these definitions are fairly simple, in fact extremely simple, so I don't think I need to illustrate them with a concrete example. And let's proceed. So now slowly we'll be going towards functions. After all, we want to talk about area under the curve. So we need to talk about functions. So fix a bounded function on the closed interval a comma b. One such function is drawn here. I've drawn a continuous function, but it doesn't have to be continuous. Right now it is just any bounded function. Recall, bounded function means that the value of this function is trapped between this region. So there is some positive real m such that for all x in the domain of f, this inequality is satisfied. That is what bounded function means. Okay, great. We define three numbers that we associate to every I. What is I? So here first, I should have written that there is a subdivision with respect to which we are having the discussion. So fix a subdivision. So sigma be a subdivision of the closed interval. Okay, and now we define three numbers and all of them depend on f. So there should be a superscript, but if there is no confusion, if there is only one function that we are talking about, we will occasionally drop this qualification in the notation. Okay, so what is meant by this number? This is defined as, I'm going to write something and then explain. The supremum of all the values that the function takes in the ith part of the subdivision. So pictorially, this is the ith part of the subdivision. Let me shade it maybe. You consult the function on this part, ask what are the values that you take the supremum of that. So in this picture, it is kind of this value, something like that. So that's the value of MIF. Similarly, little m, when we use little m, it is the infimum of all the values that the function takes on the ith part. Okay, but what about this thing that we have written here? It is an omega with a subscript I. So it is the oscillation, the name that we give to it is oscillation. Oscillation of f over the ith part. And what is its definition? It's the difference of the above two quantities. The name is well chosen. It is informing us how much deviation is there in the function. At least it is some measure of it. If I know that the largest value that the function takes here is whatever, let's say 10, and the smallest is 3, that is one piece of information. But suppose somebody just told me that the oscillation is 7, I know that the function is a little bit wild over this region, that the difference between the maximum and the minimum is substantial, whatever substantial means. Okay, so very, very simple definitions. Again, I don't think I need to take a concrete function and a concrete subdivision to illustrate these three definitions, and therefore I'll just proceed. So now we'll talk about the upper and the lower sums and see how they are connected with our goal, which is to have the theory of area under the curve. So the same setting, we have a function f defined on the closed interval a comma b, and it is a bounded function again. We fix a subdivision of a comma b, and I haven't given any names to the elements here, so let me see if I can manage some space. Yeah, so I'll just take sigma as a0 up to an as usual. That is sigma. And now we define the upper sum of f for the subdivision sigma as notationally it is this, and again the function f should feature here somewhere in this notation, which we forego usually because it becomes cumbersome. Maybe I'll write a subscript here, but I don't know if I'll be consistent with it. So the upper sum of the function f with respect to the subdivision sigma, or for the subdivision sigma, whatever you want to put it there. I mean, the English is not important. What is it? So let's look at this picture and try to motivate or illustrate the definition here, and then we'll write the formal thing. So here my subdivision has 6 parts. 1, 2, 3, 4, 5, 6 parts. So n is equal to 6. And this is the graph of the function. Again, I've drawn a continuous curve, but it doesn't have to be. It doesn't even have to be positive. It can flail about. So when we say the upper sum of f with respect to sigma, what we are trying to capture, you take the first part, ask what is the supremum of all the values that the function takes here in this part, and that is this value. And using that value, you create this rectangle, this shaded thing. And whatever is the area of this rectangle, you keep that in mind. Do the same for the second part. What is the supremum of all the values that the function takes here? It's that. And then you have this area. And then similarly for this, the supremum of all the values is this, and then you have this area. And you keep doing this and you add all those areas and you'll get the upper sum. So I have an itch to shade it out. Right, I think I got carried away, but what can I do? So the shaded area is the upper sum, but we have to keep in mind that this is a signed area. Signed, S-I-G-N-D-G-N-E-T, signed. So if the function takes negative value, for instance, this value could have been negative, right? It's the supremum of all the values that the function takes here. That could very well be negative. So this area would then be negative. So it's a signed area. We have to be very careful. So yeah, so what is it? If we want to really write the expression for it, it is the summation, right? What is the area of the first part? It is M1 times M1 times L1. Second part M2 times L2. Third part M3 times L3, and so on. And that's what we have written. Again, I have dropped F from the so there is no F here. There's an F here which I have dropped. Maybe I'll write it this time. Already starts to look ugly. So that's the upper sum. Similarly, you can define the lower sum. So the lower sum, which I wanted to illustrate here, but I've already wasted a lot of time shading this guy. So the lower sum is summation, right? And you can correlate with the picture. And as I said, we have to be very careful that these are signed areas. These could be negative, these numbers. My picture is a bit misleading. Apologies for that. Okay, let's proceed. Now we will define upper and lower integrals. Same setting, fix a bounded function on the closed interval a comma b. The upper integral of f is defined as the infimum of all possible upper sums where we vary over all subdivisions of the closed interval. So what are we trying to capture? Any upper sum, you can think of it as an overestimate of the area under the curve, right? Let me copy a picture. Copy the picture from the left, from the previous slide. So once you choose a subdivision and you record the upper sum, you have overestimated the area under the curve. The area under the curve, pictorially if you look at, is only this part. But because of the upper sum, we have overestimated. These things are overestimations. So maybe I'll shade the overestimated part. This is an overestimate, that is an overestimate. Right? So if we take finer and finer subdivisions, which I'm sure you understand what that means intuitively. Finer subdivision meaning lots of points which are very, very close by. Finitely many points, but very close by. So that's a fine subdivision. Intuitively, the finer the subdivision, the less the overestimate. And what this number is, it's sort of the best or the best overestimate that you can do, in the sense that amongst all possible overestimates, this number is the smallest. Now this is an infimum, so it's not the smallest necessarily. But this is the best you can do to approximate the area under the curve if you were to use upper sums. Right? So the definition is intuitively well motivated, is all that I'm trying to say. Okay. Similarly, you define the lower integral. So this is the upper integral, which is the best possible upper sum in some sense. Of course, it's an infimum, so it's not the best, but whatever. So the lower integral is supremum over all possible lower sums. It's the best possible underestimate. Right? Now, before I go ahead, I just want to illustrate that these two numbers, the best possible upper estimate and the best possible underestimate, they can be different. So the upper integral and the lower integral are not guaranteed to be the same, even though the knee-jerk reaction would be that they must be the same. So define this. So we are going to see an example now. So define a function as follows. Maybe just for simplicity, I'll make it 0, 1. Fx takes the value 1 if x is a rational, 0 otherwise. Wonderful. Then what is the upper integral and what is the lower integral? So whatever subdivision you make and whatever part of the subdivision you take, what is the value of this guy? You pick a subdivision sigma, you pick an I. What is the supremum of all the values that the function takes on the ith part? It is 1 because the rationals are dense. So this is always 1, and therefore for all subdivisions the upper sum is equal to 1. Right? The upper sum is always 1, and therefore the upper integral is 1. Similarly, the lower integral is 0 because the irrationals are dense, and therefore the upper and the lower integral are different. So yeah, so it's something that we should keep in mind. We would have liked to say that these two things are the same, and that is what we report as the area under the curve, the signed area under the curve. But as we see, not all functions are amenable to that equality. And that will be the definition of integrability, or a function whose integral exists. That will be the definition that we will give later, not in this lecture. Later, we'll just say that when these two things coincide, we declare the function is integrable, and the area under the curve will be this value. Both values are the same, so whichever. Okay, let's make a small note that the lower integral is at least that much, and the upper integral is at most that much. So what is little m? Little m is the infimum of fx over all possible values in the interval, and capital M is the supremum of fx over all possible values in the interval. Very simple exercise. I mean, you can take this as an exercise. It's trivial. Okay, let's proceed. Refinements, a natural notion. We have two subdivisions, sigma and tau, of a closed interval a comma b. So we want to define the common refinement. Or before that, forget about the common refinement. First, let us define what is meant by tau being a refinement of sigma. We have two subdivisions. We say that tau is a refinement of sigma if tau as a set contains, so these are the points in tau, b1, b0 up to bn. This contains the points that are there in sigma. Bad notation. This is m. So here I wanted to write an m. Now it's a good notation. So the number of points in sigma may be different from the number of points in tau. Originally that was a typo. So sigma has m points, tau has n points. We are not saying that they have the same number of points. So we say tau is a refinement of sigma. If you think of sigma as a set, you think of tau as a set, sort of. If the points in sigma are strictly contained, not strictly, but are contained in the points in tau, then we say tau refines sigma. All that is happening pictorially is, well, you write down all the points that are there in sigma, and then what will be tau? Tau will include all the points that you've already marked out. It might have some extra points. So the terminology is well chosen. And notation, when we write this, we just mean that tau is a refinement of sigma. So yeah, just a very simple definition. And now, forget about the second part, we'll talk about that. But the first part, if sigma is refined by tau, then the norm of sigma is at least the norm of tau. So this is a very simple exercise once you recall the definition of norm. The norm of sigma is the maximum length of all the parts that are there in sigma. So sigma is a1 up to, this thing is sigma, so we're running up to m. So this is an exercise. What is this? So here we have a bounded function. We have a bounded function, and then all of these are with respect to that function. So we are claiming that if sigma is refined by tau, then the lower sum of f with respect to sigma is at most the lower sum of f with respect to tau. So why is that? Let us try to understand this in the simplest possible case, and that should make it clear how to prove it in general. So we have the interval a comma b. That's the interval, and let's say sigma is just the most trivial subdivision where a0 is a and a1 is b, so there is nothing in between. And tau is whatever you like, so it's b0 and then a b1 and b2. So b1 is somewhere here. This is b0, that is b2. So for sigma, or for the lower sum of f with respect to sigma, what are we doing? Let's say function has some, let me try to draw some function. So what is this number? This is the infimum of all the, infimum or the only part that the partition has, and that multiplied by the length of the part. So that is this value times this length. All right, so maybe I'll shade it. This shaded part is the lower sum with respect to sigma. What about the lower sum with respect to tau? So there we will take the infimum over this part and multiply with this length, and infimum over that part and then multiply with that length. But both these infimums are definitely at least the infimum of the function over this entire thing. If you take the infimum over a smaller region, you will obtain a possibly bigger value. You cannot obtain a lower value. The bigger the region you take to take the infimum, the smaller the value you get. So over this region, the infimum is at least the infimum over the entire thing, and that you're multiplying with this length. And over this region, the same comment, and that you're multiplying with this length. So you're getting at least the global infimum times the total length. I don't want to write all of that. So that should be enough for you to convince yourself. If we really want to draw a picture, let me extend. So the area for the first part of tau, that will be this much, this rectangle. And for the area of the second part, it will be this much. Because the infimum of the function on this part is this value. So this area plus that area is clearly at least that area. So whatever, I mean, you can easily understand this. And similarly, you can prove this. So the lower sums preserve this kind of inequality, if you like. The upper sums flip it. Okay. So now, common refinement. Fix two subdivisions of a comma b. The common refinement of sigma and tau is defined as the subdivision is the subdivision sigma union tau. Now what am I saying? So for this definition, think of sigma as a finite subset of a comma b rather than an ordered thing. It's just a finite subset of a comma b which contains the left and the right endpoints, and similarly for tau. So you can take their union and you again obtain a finite subset of a comma b which contains the left and the right endpoints. So that is the common refinement of sigma and tau. Pictorially, I have drawn sigma and tau, some example of them. What is sigma union tau, or what is the subdivision that we mean when we write sigma union tau? We mean just coalesce the two. Just coalesce the two and erase the hodgepodge. So all these points that you get is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th. So you, or maybe there is one more here hiding, but that is because of my, bad translation. Whatever, I think you get the point. So you take the union of the two sets, you get another set which contains both the left and the right endpoints. And maybe I will translate it one more time just for my peace of mind. This better coincide with that. And now it's a little better maybe. Anyway, so this is sigma union tau, the thing that you see. So I hope the meaning of common refinement is clear. Even the terminology should have made it clear. So what are we trying to say? We are saying, suppose sigma and tau are subdivisions of the closed interval a comma b. Then the lower sum with respect to sigma of the function f is a bounded function on the closed interval. Lower sum with respect to sigma is at most the upper sum with respect to tau. So sigma and tau are arbitrary subdivisions. We are not saying tau refines sigma or any such thing. But the lower sum is always less than or at most the upper sum, no matter what subdivisions you pick. So that's very nice. Intuitively, this is clear if you just think in terms of pictures, but we need to prove it. And the proof is very simple. The proof is just let rho be the common refinement of sigma and tau. Then we know the lower sum of f with respect to sigma has this property because rho refines sigma, and we just saw in the previous slide that the lower sums behave well with respect to this. So we have that. And the upper sums flip the thing. Tau is coarser than rho. Rho refines tau also. But the upper sums flip that the refinement thing. So here I will write this thing. And that's it. We have the requisite inequality. The lower sums are always at most the upper sums. All right. Yeah, I think that's all. So this in particular shows that the lower integral, so this shows that the lower integral is at most the upper integral. Once you have this, you immediately obtain that. So this is also a lemma, but I am not writing this as a lemma. Just take this as an exercise. Here you will take supremum over all sigmas, here you will take infimum over all taus, but this inequality is always true, so will be preserved even when you take supremum here and infimum there. So the lower sum, the lower integral is at most the upper integral. The upper integral, I have somehow forgotten to put the bar. Lower integral is at most the upper integral. Okay, great. So this is all that I wanted to say. As usual, like, comment, share, subscribe, and I will see you next time.